Hello, SPH3U. This is the first online video lecture thing. First things first, please look down below the video for the timestamps, because I'm just going to be blabbing on about video lectures for a little while. If you want to just jump right into the physics, hit that timestamp down below, and we can jump right into the problems. Let's have a look at our learning goals today. Number one, we're going to get used to video lectures. I'm going to talk about these lectures and how I'm going to run them. Number two, we're going to review work and energy, because it's been like a week since we've seen them, so I figured that would be useful to review those. And then we're going to review just the equations for gravitational and kinetic energies, do some problems with that, and finally get to what we were doing on Thursday, which is conservation of energy, converting between gravitational and potential with and without mass. So let's have a look at our current topic. Down there. That's going to stay on screen. It's getting information from sinusoidal functions. So put that away. So getting information from, it's not getting information from sinusoidal functions. I'm sorry. That was from the last video. I was making a math video. Our current topic is actually getting used to video lectures. I forgot to save that. There we go. We're getting used to video lectures. See, I'm still getting used to video lectures myself. So let's talk about this video. This video, number one, is not mandatory for your hours. And let's talk about those hours. You know, this is the why am I doing video lectures. So why video lectures? Right, why video lectures? Well, number one, it's easy to track attendance. Right, first off, easy to track attendance. I'm just going to have EDSB quizzes for each video. So EDSB quizzes for each video. Completing the quiz successfully, one quiz equals 1 hour. If you complete the quiz successfully, you get 1 hour worth of time. Number two, the ministry. The ministry wants proof. The ministry wants proof of me teaching you stuff, and this is a really easy way to do that. Specifically, the ministry wants 10 hours a week of content. Right, 10 hours a week of content. And for me, that's going to be 5 hours video lectures, 5 hours of video lectures, and 5 hours of direct, of live help sessions. So we're going to have 5 hours of live help sessions where I'm going to be available on the Zoom platform. I've decided to use Zoom because I like the options there. So we're going to do that on the Zoom platform. You'll have a meeting and you'll have to, you'll have to log in and do live help sessions. So the Zoom rules to get your 5 hours. Zoom rules to get your 5 hours. We'll actually do a little. Zoom rules to get your 5 hours. You have to log in once a day. Right, log in at least once a day. You have to participate at least once a day. So that's anything from asking questions to making a comment about the content, to doing a practice problem with me, whatever. As long as you participated in the class in some way, you're going to get that. And it's a total of 5 hours for the week. So I'm going to track how many hours you have for the week. It doesn't mean 1 hour, 1 hour, 1 hour, 1 hour. Pick and choose which lecture you want to spend more or less time on. Sometimes you'll just be like, yeah, I got this. Sometimes you'll be like, oh, I need more help with this. So, that isn't to discourage you from spending all the 10 hours on Zoom, because I'll be there during normal class time for help. So, if if you want to spend more than the 5 hours, I would be very happy with that. Teachers always like talking to their students. We always like helping people out if they need help with stuff. So that's the ministry that wants proof. And number 3, making these videos is not super convenient for me, but it's super convenient for you. All right, it's super convenient for you. We've already talked about timestamps below the video. All right, timestamps are going to be below the video. I can add links in the description. Links in the description. And because it's a YouTube channel, it's easy to organize content on the channel. Right? It's easy to organize content on my YouTube channel. So that's why I'm doing video lectures. That's why we're doing this as content delivery. I've been talking for about 6 minutes now. Just a sec. I've been talking for about 6 minutes. It's time to kind of show off a little bit of this setup. Please keep this in mind, the 10 hours a week of content in particular. Make sure you know your responsibilities for the Zoom sessions that are going to start on Monday. And note that this video is only a practice video. This video does not count towards those attendance quizzes or anything like that. Okay, let's show off a little bit. So I'm going to pull that away. Oh, no, pull that away. Pull that away. That goes away. And let's show you some of these views I've got. So first off, we can go to just straight up to the desktop. This is the desktop, but that's kind of boring. You want my face, so here's my face down in the corner. Hello. If I'm blocking something important, like down here, I've got I'm blocking that down there. I can also put my face up on that side. I can put my face on that side, and then I'm not blocking that down here. So that's the first kind of cool thing. I can go to just my face, as you've seen before. And then I've got a camera over that way. So here's this camera. Hello. This is for wider shots, if I need to throw something, as I'm fond of doing in physics class, throwing something to make a point. I can do that here. And it's pointing at this. And this is one of Miss G's whiteboards. So thanks, Miss G, for your generous donation. Why that's there is, I'm not going to be, I felt like it would be awkward to do this all the time. That seems bad. So what I've done, and I'll kind of show you the setup here, it's kind of clever, is I've stolen one of our science lab's stands, and it's got a camera on it, so that camera is pointing down, and it's looking here. Let me turn off that calculator for a sec. That's looking down at the whiteboard, and so you've got this camera down in the corner, you've got the screen over here that I can turn on and off, and then you've got my hands, so I can draw things. This way you don't get into those awkward, like trying to make a formula on the computer. I can just be like, EK is mv squared over 2, and there it is right on there. It's a whiteboard, and I've stolen markers from Blythe as well. So those are the views that you can expect. That's how video lectures are going to look. Not much else to say there. So going back over our plan here, our learning goals, getting used to video lectures, already done, and that's 9 minutes in. We're going to move on to reviewing work and energy concepts, which means I get to change the current topic. Reviewing work and energy. Reviewing work and energy. And the keep in mind is going to have to change too. Keep in mind physics definition of work versus, for lack of a better word, normal definition of work. So keep in mind, and we'll change. Keep in mind that. Tick away those learning goals, and we are reviewing work and energy, and we're working on that review. So to do that, I'm going to jump over to this view, and we're going to talk about some conceptual questions focused on conservation of energy. And here is something from a online textbook. Take away the table of contents, and this is an online textbook. So it says here, consider the following scenario. A car for which friction is not negligible accelerates from rest down a hill, running out of gas after a short distance. The driver lets the car coast further down the hill, then up and over a small crest. He then coasts down that hill into a gas station where he brakes to a stop and fills the tank with gasoline. Identify the forms of energy the car has and how they are changed and transferred in this series of events. So that's work and energy. We're going to go over to our whiteboard view and kind of copy that diagram. So we have a car, it is going down a hill, comes over the hill, down and into the gas station. I'm going to move my, that's not what I want to move. This is what I want to move. Here we go. Move that up to the corner so that you see a little bit better. Right, we've got the car. We have these sections here. This is where it starts coasting. This is where it comes up the hill. All right, comes up the hill. There's the bottom of the hill. It coasts down the hill, and then it is stopping to get gas at the gas station. So first, let's identify the kinds of energy that we're interested in, and there are three kinds of energy that we normally talk about, and that is kinetic energy, gravitational energy, and internal energy. Right? Internal energy is everything else. So EK, EG, and internal energy. EK has the physical quantity speed associated with it. EG has the physical quantity height associated with it. Internal energy is everything else. And then we've got lost, quote unquote, lost energy, which basically is heat to the surroundings. Heat to the surroundings. All right, lost energy. So let's talk about this. This question says that friction does exist, that friction is important. So what we're interested in, we'll just jump back to the desktop for a second. It says, consider the following scenario. Friction is not negligible. Question is, identify the forms of energy the car has and how they are changed and transformed in this series of events. Back we go to the camera view. I'm going to take away the screen so that we see a little bit better. So let's talk about what we want. So number one, identify forms of energy. And number two is how they are changed and transferred. How they are changed and transferred. How they are changed and transferred during this sequence of events as the car coasts down the hill and comes to a stop. So, first question is, where does the car have the most energy? Where's the maximum energy of this car? Take a minute to think about it. And I mean, clearly it's up here. Here's the maximum total energy, maximum energy. Right, max energy up here, max energy up there. The reason that that's the max energy is that all along this entire hill, you have energy lost to friction. Energy quote-unquote lost to friction. What we mean, of course, is that it has moved into just heat that's gone out of the environment. It heats up the tires, it heats up the air, it heats up the road, and then it just leaves. We can't recover it, no matter how hard we try. So that's max energy. Let's talk about transformations. During this stage, from part 1 to part 2, we go from EG to some EK. There's still some gravitational energy, so plus some EG. Right, so this is all EG, I guess. It's all EG there. This is some and some EG plus heat, right? Plus some just heat that's gone out into the environment. That looks like a game or something. Some EG plus heat. Then on the way up, right? On the way up, we'll go green. On the way up to here, we have more EG because it's gone up, less EK. So we've got gravitational turning into, kinetic turning into gravitational, and plus more heat. And then on the way down, it's going to, on the way down, it's going down to, we might call that 0 EG, no EG, more EK, and the max heat. We've lost the maximum amount of energy at the bottom there. And then it's important to note in the question that it says during this time they take gasoline and pump it in, right? Gas goes into the car, and that's plus chemical energy. So we're kind of increasing the internal energy of the car along the way. So this is forms of energy. This is how they're changing. That chemical energy could, I guess, technically be considered internal energy. Is that? That's kind of looking at me. Okay, yeah, that looks better. Okay, so that's the first question, is reviewing energy. We've done that. Let's move on to work. Let's talk about the work energy theorem. I've got some questions for that. I've got some practice questions for that. Let's go over here, back to our book, and we're going to go to conceptual problems and exercises, and we're going to talk about the work energy theorem. And the point here is the physics definition of work is not the same as the normal definition of work. Right. So let's try a practice problem here. Remember that in physics, work is defined as the change in energy, or work is defined as force times distance. So let's try this one here. Calculate the force needed to bring a 950 kilogram car to rest from a speed of 90 kilometers an hour in a distance of 120 meters. There's a typical distance. Or suppose instead the car hits a concrete abutment at full speed and is brought to a stop in 2 meters. Calculate the force exerted on the car compared to the force found in part A. This involves our kinetic energy formula, and it involves our work equation. So I'm going to stick this over to the document camera. Here we go. So let's put the situation in perspective. We have a car. It's going to be a circle because I can't draw cars. Coming in at initial speed of 90 kilometers per hour. The car weighs 950 kilos. And it needs to stop stop in a distance of 120 meters. Stop in a distance of 120 meters. And it's asking us to figure out how much work is done. Well, work here, we use our first formula for work. Work is the change in energy. What kind of energy has changed here? Well, it hasn't gained height or lost height. So the only change here is kinetic energy. Let's change in kinetic energy. And over here, EK is mv squared over 2. And over here, EK equals 0. So if we just figure out how much kinetic energy it had at the start, we'll know how much energy it lost and how much work was done to it. So, so let's do that. The first problem is if we want our work to be in joules, that can't be in kilometers. Now we're going to convert it to meters a second. So we want to convert it to meters per second. The trick for that is we just divide by 3.6. So let's figure that out. Let's figure out what 90 divided by 3.6 is. Pull up a calculator here. Let's look at our calculator. 90 divided by 3.6 equals 25. Well, that's handy. All right, thank you, calculator. You've served us well. So 3.6. It is 25.0. We have to keep our sig digs. 25.0 meters per second. The 3.6 is exact. So as many sig digs as we want in that 3.6. So 25 meters per second. It goes. That's our starting speed. Let's figure out the EK. It's mv squared over 2, which is 950 kilograms. That's already in SI units, times 25.0 meters per second squared over 2, which is going to give us 950 kilograms times 25 times 25 is 625 meters squared per second squared. All that over 2. Now that one I can't do in my head because I don't know it. So we'll pull up the calculator again. Calculator, and we're doing this equation here. 950 times 625. So 950 times 625 equals that, and we divide it by 2 equals that. 296,875 joules. 296,875 joules. Or approximately, because we need sig digs, we have 2 sig digs because the 950 has 2 sig digs. 1, 2. 2 sig digs there. There's 3 sig digs here. So 2 sig digs here is going to be 3.0 times 10 to the 5 joules. We have to do it like that because otherwise we don't have our 2 sig digs. Right? If we rounded it to 300,000 joules, that's only 1 sig dig. We have to do it like this. Yeah, I don't like it when they do that to us. That's annoying. So that's how many joules, right? The work. So work is 3.0 times 10 to the 5 joules. Right, we got that from how much kinetic energy it lost. Because it started with kinetic energy, it finished with 0 kinetic energy. So it changed in kinetic energy by that much. Take away the calculator. And that's a work problem. Now the problem's asking us also to use this distance to figure out how much average force it took to stop the car. So to do that, we need the other equation, which is work is force times delta distance. Force times distance. In this case, the force is going to be a force of friction, and the force is against the motion. The displacement's this way. Displacement's this way. The force is that way. We're going to end up with negative work. So, you can tell that this is going to be negative. We started with kinetic energy and then we finished with none of it, so that's going to be negative 300,000 joules. But force times distance, we have to rearrange this because we're looking for the force. What's the force? The force, to rearrange it, it's times distance right now, times displacement right now. So bring that over by dividing by displacement on both sides. We're allowed to do that, which means that this reduces to 1. Therefore, force is equal to work over distance, which is negative 3.0 times 10 to the 5 joules divided by 120 meters, which is approximately 3 divided out by 120. Let's solve that. So pull up our calculator. 3.0 times 10 to the 5. 3 times 10 to the 5 divided by 120. Right, there's 3 times 10 to the 5, there's 120. That's equal to 2,500. So 2,500 newtons, because we're looking for a force, and force is in newtons. 2,500 newtons. And thankfully that's already got 2 sig digs, so we're good to go there. Let's turn off the camera, the calculator, by the calculator. Yeah, so that's how you would be able to figure it out using, oh, that looks like an energy. Force is work times distance, or work over distance. So the work energy formula is useful because you can see how changing the distance is going to change the amount of force needed. If we had a short distance, it asks us to do it with a 2 meter abutment? Yeah, a 2 meter abutment. So instead of having a whole 120 meters to come to a stop, it just goes and just stops. What that would change would be in our expression here, instead of 120 meters, we would be stopping in 2 meters, right? So we keep the same amount of work because we're losing the same amount of kinetic energy. It's still going to a stop, but now it's doing it in 2 meters. I believe 2.00 meters in the question, and that brings it down to 150,000 newtons. Right, reducing the distance increases the force by a lot. This is why cars have crumple zones, right? If you think about a car, if you ever watch a modern car in a car crash, it kind of starts off looking like this, and then the whole front of it scrunches up as it hits the wall. And it looks really bad, but the whole point of that is to increase the distance, because if the whole thing stayed straight, it's like, just hitting the wall instead of slowly absorbing the impact in the wall. Yeah, so that's work and energy. That's the work energy theorem. I think that's enough talking on that front. I think we have done our goal. We have gotten used to it. We're reviewing work and energy concepts in terms of changes of energy and in terms of using the work energy theorem, using those 2 formulas for work. Work is the change in energy, and work is force times distance. Now we're going to review the kinetic and gravitational energy equations so that we can use them to solve problems. So let's change that to our current topic is reviewing kinetic and gravitational energy equations. So we'll change our current topic, and keep in mind here is mass should be in kilograms, speed should be in meters per second, and height should be in meters in order for all of this to work. So there's our SI units. We want to make sure that those are in SI. And if you do all that correctly, then the energy is in joules. The energy becomes joules. Okay, so let's get to reviewing gravitational and kinetic energies. Once again, I have some I have some practice problems for this. We did one for kinetic already. Let's do a gravitational one. How about this one? In a downhill ski race, surprising little advantage is gained by getting a running start. To demonstrate this, find the final speed and the time taken for a skier who skis 70 meters along a 30-degree slope, neglecting friction. So we're just going to do the final speed. Neglecting friction. A starting from rest, B starting with initial speed of 2.5 meters per second. So we're going to do this question here, and we're going to take a look at it over on the whiteboard. So let's go over to the whiteboard. And here's our scenario now. Our scenario is a skier who skis down a slope. The slope is 70 meters long. 70 meters long. 70 meters long. The angle of the slope is 30 degrees. And we have to do it twice. First off, starting from rest, VI equals 0, and second off, VI is 2.5 meters per second, I believe is, 2.50 meters per second. So that's A and B, so A and B. So the first thing is to remember that energy has no vector. Energy is scalar. So all that this cares about, all that the energy cares about, is how high up the skier is. So height, right? Height is what matters. Height is gravitational energy. Height is gravitational energy. To figure out how much gravitational energy they lose, it's mass times gravity times height, m times g times h. So that's how much gravitational energy they lose coming down the hill. But we have to figure out the height. Right? It's not 70 because that's on the slope. How do we figure out the height? Well, there's a 90-degree angle here. So we can use trig. Okay, this is a 30-degree angle. This guy, if we pull out a different color here, this is the hypotenuse, this is the adjacent, and this is the opposite. The hypotenuse, the adjacent, is the opposite side. So since we want the opposite side, we're going to use sine. So sine theta is O over H. That's the SO in SOHCAHTOA. In this case, then the opposite, which is what we want, to rearrange, we're dividing by H here, so we can multiply by H on both sides. So let's multiply by H on both sides, times H times sine theta. And we are going to, this reduces to 1, therefore opposite. Therefore the opposite, which is what we're interested in, is H times sine theta. And in our case, that is 70 meters, 70.0 meters times 70. Which is 70.0 meters times sine of 30 degrees. Right, 70 meters times sine 30 degrees, and that's to figure out the height. So 70 times sine 30 happens to be 35.0 meters. I believe it is 30 degrees, which I think was just an oversight for them for sig digs. Otherwise, this would have to say 40 meters. With our get even rule. Let's just pretend that this is accurate to the degree, and we'll just call it 35. Now split the difference. So let's say it's 35 meters. So that tells us our height, 35 meters, some basic trig to get our height. Now that we know how far it's dropped, we know how much gravitational energy it's going to lose, because we know G and M, once we set up the problem correctly, is going to cancel out. So let's do that. Let's actually set this up. At the top, in scenario A, at the top it's all the EG. At the bottom, it's all EK, because there's no speed at the top. Therefore, if there's no friction, which is the problem told us not to do any friction, the M times the G times the H at the top is going to equal the M V squared over 2 at the bottom. M is going to reduce to 1 here. We're allowed to do that. It's essentially just dividing by M on both sides, right? If we think about it that way, divide by M. So divide by M, and the M's cancel out. We'll just erase that. Which gives us our new equation, GH equals V squared over 2. We're actually looking for V, so let's get rid of this 2. We multiply by 2 on both sides. 2 times GH, 2 times V squared, that cancels out, but that leaves this 2 over here, so 2GH equals V squared, and then all that's left is to square root that. So the square root of 2 times G times H equals V, the speed of our skier. We can solve that. We know H is 35 meters. We know G, because we always know G, and 2 is just 2. So let's actually do that. 2 times 9.81 meters per second squared times height, which we decided was 35 meters, equals V. I need to get the calculator out. So let's get that calculator out. Calculator. We're doing 2 times 9.81 times 35 equals 686.7. So that's the inside, that's still in the square root. 686.7, and it's meters squared per second squared, because meters times meters here is meter squared, and the second squared stays around, is V. Then we're going to square root that, so let's just go ahead and hit the square root button on our calculator. Square root is here. 26.2. 26.2 meters per second is the speed. In situation A, where the initial speed is 0 meters a second. That's the initial speed up there. Now in the second case, it's asking us to figure it out when the initial speed is 2.5 meters per second. That's final speed 26.2. It's asking us what happens if the skier starts with 2.5 meters a second of speed. And you might be tempted to just go, well, if it started with 2.5 and it's gaining 26.2 meters a second, then, isn't it just 26.2 plus 2.5 meters per second? Right? And you would be wrong, because the square root will get in your way. Because you can't really just straight up add things that way. Kinetic energy is interesting. The square will make it so that twice the speed is actually 4 times the energy, and 3 times the speed is 9 times the energy. So it doesn't add up the way you think it does. Let's prove that. Let's actually prove that. We can actually recycle some of this, because the only difference to what we had before now is it wasn't just MGH, it was MGH plus MV1 over 2 is going to be equal to MV2 squared over 2. Just a sec, I'm going to pause. sorry about that. I got a phone call from the tech support people. So yeah, MGH. Here, this h is the height at the start. The height at the start. This v1 squared is this v1, which is 2.5 meters a second, and v2 is going to be our speed at the bottom. So again, it's a very similar setup, except for we have this extra mv squared over 2 term, which makes it a little bit more annoying. Same thing happens, the masses will reduce to 1. But now when we do our rearrange here, it's going to be g times h plus v1 squared over 2 equals v2 squared over 2. If you think back here, the one thing we did was we multiplied things by 2. We can still multiply things by 2, but now we have to multiply everything in here by 2, every single term by 2. So it's going to be 2 times gh, this times 2, and this times 2. Those 2's are going to reduce to 1, those 2's are going to reduce to 1. But that means we keep this v1 squared. So 2 times g times h plus v1 squared equals v2 squared, which means now we have an extra term. We're interested in v2, we're still going to square root everything. That square root has to encompass this whole thing, 2 times g times h plus v1 squared equals v2. We can still pull this same thing here, right? This is still 2gh, but we also have to add this v1 term, so v1 squared term. So that's the square root of, we're going to pull just this number straight up because we already calculated it earlier, 2.7 meters squared per second squared, plus we have to square 2.5 meters per second. We have to square that, equals v2. And what we're going to get is the square root of 686.7 meters squared per second squared plus 2.5 squared is 6.25 meters squared per second squared equals v2. And it'll be the square root of 286.7 plus 6.25, which is 692.95 meters squared per second squared. I just do that in my head. All right, we're just adding those two together equals v2, and then the actual square root. There, we're actually going to take the square root of that number, and that is equal to, v2 is equal to, let's actually do a square root. We'll pull up the calculator, and clear. It is 692.95, and we're going to square root that. 26.32 meters. 26.32 meters per second. Meters per second is the new v2. Right? It's changed by a whole, look at that, a whole 0.12 meters per second. So that just goes to show you can't just add the 2.5 starting, remember that our starting was the 2.5 meters a second. We can't just straight add it to this. We've only actually added 0.12 meters a second because kinetic energy doesn't add up the way that you think it does. So the equations are the important thing here. So in this review then, what was important was the way that the kinetic and gravitational energy equations respond to each other, and the fact that the gravitational energy equation is only on height, just height. So we need to figure out the height that something drops through. I'm not going to give you something like this on a test. That's a little bit overcomplicated. I would lead you through each individual step, but it's still interesting to see just how little of an effect that starting sprint has on our skier's final speed. Let's jump back over and go back to our learning goals. We reviewed kinetic and gravitational energy equations, and we actually did a conservation of energy problem. So I guess that means that's the end of this video. Hopefully that gives you an idea of how I'm going to run these video lectures, and it's just about 45 minutes, so I'm going to sign off. Thank you very much for watching, and see you in the next video.